digit queries problem from the CSES problem set. So here we consider an infinite string that consists of all positive integers in increasing order. So 1, then it's 2, then it's 3, and so forth, okay? So we essentially concatenate all of these numbers to get the string. Your task is to process Q queries of the form, what is the digit at position k in the string? The first input line has an integer q, the number of queries. After this, there are q lines that describe the queries. Each line has an integer k, one based index position in the string. So for k equal to 1, we will output 1, okay? And not 0 or anything else. And for each query, we have to print the corresponding digit, essentially. We have at most 1000 queries, and the index of the digit will be at most 10 to the power of 18. And this is the sample input-output pair, which you can test using this string here, okay? Now, let's look into the solution. So what we will be doing is to split the problem into 3 subproblems, okay? Which will help us eventually solve the problem. So the first subproblem is to identify the length of the number in which my digit belongs to. The second part is to actually identify the number, okay? So I save this into a string that I call n here, okay? So the string called number will will actually store the exact number in which our digit belongs to, and that will be done digit by digit. So we will begin from the most significant digit until the least significant digit and identify the number, okay? And after we have identified the number, k will actually have the leftover indexes, and we will use these leftover indexes to output the exact digit that we have been initially searching, okay? So these are the 3 parts of our solution. So to solve this problem, I use some functions here, which we will be looking right now, and then we will be using them abstractly, okay? So the first function that I'm using is myPow, which calculates powers essentially. So x to the power of p, if p equals to 0, we return 1, which is the base case. So x to the power of 0 equals to 1 essentially, okay? Otherwise, in the general case, we split the function into 2. We split the calculation, the power essentially into 2, so p divided by 2. So we reuse our function. Again, the base remains the same, so x, and the exponent becomes p divided by 2, so the half of what we are searching. And because we are using integer division here, if p is an odd number, that's what this is testing here. If it is an odd number, we're going to return the result of that we stored into this half variable, multiply it by itself, and multiply one more time with x, okay? So for p equals to 5, 5 divided by 2 with integer division will be equal to 2. So x to the power of 2 times x to the power of 2 is equal to x to the power of 4. So one more power will give us x to the power of 5, which was what we initially were searching, okay? In the other case, where p is an even number, we just multiply half with half again. So that will give us the answer, okay? Because if p is even, we're not going to lose any power by dividing by 2, okay? So now let's look into this L2D function. So initially the name was intended to mean length to digits, but that doesn't really matter, okay? So let's just call it L2D, okay? That's the other function that we will be using abstractly. So this function has 2 definitions. One is just with 1 variable. The other one is with 3 variables. So let's look into the first one. So what we intend to calculate here is the number of digits that numbers with this amount of this length have. So beginning from the lowest one, so let's say that length equals to 3. The lowest 3-digit number is 100. The highest 3-digit number is 999. So in this range of numbers, we need to calculate how many digits we have. So the result here will be 999 minus 100, which is the lowest one. So that gives us 899 plus 1, which is for this number here that we haven't counted. So 900 integers, essentially, 900 different numbers. And all of these numbers, they contribute 3 digits to the number of digits that we need to remove from our index, okay? So 3 times 900, that will give us 2,700 digits being contributed from all the 3-digit numbers, essentially, okay? So how do we calculate this? Is we use combinadorics. So for the most significant bit, we have 9 options because we exclude the option of 0. The most significant bit cannot be equal to 0. And for all the other positions or indexes in our number, we have 10 options because we include the option of that number of that digit on that specific index being equal to 0. Okay, so here the range is from 1 until 9, and here the range is from 0 until 9, essentially. And we have, for every such digit, we have 10 options. So it's going to be 10 times 10 times 10, length minus 1 times. So the minus 1 here is because we have already considered the options for the most significant digit. So we remove that from the length, and that will leave us with all of the indexes that have 10 options for their value. So we multiply this to essentially get the numbers in this range, okay? And then by multiplying with the length, we will get the digits of the numbers that all these numbers will contribute, essentially, okay? And that's pretty much it for the first definition. So for the second definition, it's a more elaborate one. So for this one, we can look into the examples to get a better understanding of what we are trying to output here. So x will essentially be the index of the digit that we are for which we are going to set a specific value. Okay, so x will be equal to the length if we are looking at the most significant digit, and it will be equal to 1 if we are looking at the least significant digit. Okay, so x being equal to 3 and set being equal to 5. So the value that we will set for that index being equal to 5 and length being equal to 6. This will give us how many digits, okay? So we will calculate how many digits we have in the range between this number and this number. So what the D represents here is the digits that we don't care about. We have already discovered those digits, so we don't care about them. The only digits that we care about is beginning from the index that we are going to set into a specific value until the least significant digit, essentially. So the least significant digit has an index of 1, okay? So from 3 to 1, essentially, in this case, in this particular case, we're gonna find the lowest, so all the zeros, until the highest, okay? So the highest here with the number being set, so being set to 5, and all 9s afterwards, okay? So how many numbers do we have here? That's what we need to find out. And then we just multiply this with the length of our of these numbers. So in this case, it's the length that each number contributes is 6, okay? In this other case here, we have exactly the same parameters, but this time the index will be pointing to the most significant digit. So in this case, instead of all zeros, we're going to have this set to 1, okay? And we're going to reach again the value where we set our number to what we intended to set it to, and all 9s afterwards, okay? And again, we will be multiplying by 6 for every number that we have here. The last example here has a smaller example here for you to grasp this better. For x being equal to 1, we set the digit to be 5 and the length, actually here the set should have been 9 because I'm setting it to 9 essentially. If it was 5, this would have been 5 as well, okay? So the range that we calculate the digits for is D, and then we have the lowest number, so 0 in this case, and the number that we're going to set is 2. So if this is 5, this should have been 5 as well. So this would have been 5 different numbers, every number contributing 2 digits. So 2 times 5, this will have given us a result of 10 essentially, if this was a 5. So let's look at how we calculate this essentially. What we do is we look at our value that we are going to set. Okay, so in this case, let's look at the first case, okay? So in this case, we have the value to be equal to 5, okay? Now we are looking at the index, and if the index is equal to the length of the number, it means that we are pointing to the most significant bit. So if that's the case, we're not going to consider any more values. So if it's 5, we're going to consider 5 values. So from 1 until 5, we have 5 different values that we can pick from. Otherwise, if we are not looking at the most significant bit, we can also pick the value of 0. So here, in this case, where we're not having the most significant bit, we begin from the point where this value is set to 0. But in this case, we begin from the point where the value is set to 1, okay? So because it's the most significant bit, it cannot be set to 0. So this essentially is an if statement, and if it is the most significant, we add 0. Otherwise, that's what this means, we add 1, okay? So this first parenthesis counts how many options we have for the bit that we are going to set. Now we just need to calculate, let me just do this like this, yeah. Now we just need to calculate for the other digits, which are less significant. So x minus 1 will give us the number of these digits. How many options we have, and for every individual one of them we have 10 options. So 10 times 10 times 10, x minus 1 times will give us that number, okay? And this essentially will give us the numbers that we have, and we multiply by the length to get the digits that the numbers in this range will contribute, okay? So how many digits will this range, for example, contribute, so that we subtract, so that we're going to subtract those digits from k to get the index, okay, that we are looking for essentially. Now let's look into the actual solution here. So we just read a k here for every single, this is just the solution for every single query that we are looking at. So for every single query, we read number k here. Then to determine the length, we set the length to be equal to 1 because our number cannot have a smaller length than this, okay? It's going to have at least 1 digit. And then we just subtract from k the value of digits for this length, okay? Which we have already seen that we calculate using this function here, okay? And if this is greater than 0, it means that the number of digits in this range for this length are not enough to cover the index that we are searching for, okay? So what we do is we subtract those digits, okay? So we recalculate this and we subtract this from k, and we increase the length of our number essentially, okay, by 1. So we know that we are looking for 2-digit numbers if 1-digit numbers cannot cover our index. So for k equal to 12, for example, 12 minus 9, because we have 9 1-digit numbers contributing 9 digits. 12 minus 9 equals to 3, which is greater than 0. So we know that now we should be looking into 2-digit numbers. We increase by 1. And we repeat this until we have seen that the number of digits is enough to cover the index that we are looking for. Now, after we have after we find out how many what is the length of the number that we belong to, we now will unveil digit by digit, beginning from the most significant one until the least significant one. So the most significant one has the index of the length, and the least significant one has an index of 1 essentially. And we will be calculating those digits one by one. We will be unveiling them one by one and updating this k variable here, okay? So that it will point to the digit for which we are searching for. And the string, which we call number here, will initially be empty, okay? So in the string, we will save all of the digits of our number. Now we are searching from the lowest possible digit up until the highest possible digit. Here I'm using binary search. You can, instead of use binary search, you can just do this linearly. I'm just doing this to optimize my solution essentially. So for every digit, I will be needing a logarithmic time to find out what that digit is. Otherwise, you would need linear time, okay? But anyways, let's look into the binary search here. So until, as long as left is less than right, okay? So we haven't found our index. We calculate this mid variable here. So left plus right divided by 2. This is just a common binary search line essentially. Will give us the value for that digit that we are going to currently test. So how do we test this? So we get k minus the LTOD function, which we explained, for the previous value of mid, so -1. So for one value lowest, that value should not cover the index that we're looking for, okay? And the value that we have, though, should actually cover it. So if k minus the number of digits in this range is smaller or equal to 0, it means that we are either covering it completely or we have exactly cover this index, okay? In that case, we set mid to be the value that we will be returning. So mid equals to right equals to left. Actually, here I could just say left equals to mid. This is just unnecessary here. And then we would break the loop, okay? So we would break the binary search. In any other case where either this one is not true or this one is not true, so the entire if statement here becomes false. We check if the value that we have right now, if that value is not sufficient. So if k minus the digits that we will be removing is greater than 0, so we are not covering that index, we increase that value by 1, okay? And we save it to left. And we just continue our search. Otherwise, it means that this value that we have, the mid value, is actually too great, and we will be missing the actual value that we are searching for if we keep this into our range. So now we just update right to be equal to mid -1. Okay, so we are searching for lower values that will suffice for the range of digits, for the range of numbers that will cover the number of digits that we need to cover this index here, this index k. And after we have found the exact digit for this position I, okay, we simply add this to our string. So we save the digit we have just unveiled by adding the value that we found to the character for 0, okay? And then we just subtract from k the value which is given from the function that we have already inspected before. So for left -1, so if we look into this function here, if the digit that we have found out that works for us is 5, we need to subtract all the numbers from 000 until 499, excuse me. And then we will be left with all the numbers from D 500 until D 599, okay? So this digit will also be searched. So for future calls of this function, this will also be D essentially, okay? And we will be looking at indexes, at smaller indexes that we are going to try to set essentially, okay? Now, we just remove, as I said, we just subtract this from k so that the indexes left into this indexing variable k will be regarding to the position that we're currently in, okay? And then after we have unveiled that number, we can use the leftover indexes to output the exact digit that we care about. So k -1, because the string number here essentially uses 0-based indexing and we are using 1-based indexing. So we just remove by 1 here. And we simply output this. So again, we break the problem into 3 parts. Let's look into these parts one more time and close this video. So we find out the length of the number. Then based on that length and the indexes that are remaining, we unveil the number, we unveil the final number that our digit belongs to, digit by digit. So beginning from the most significant digit until the least significant digit, we just do binary search here, or you could do this linearly. And for this case here, where it means that our value is such that it covers the index, and if we picked the previous one, it will not cover the index, which means that this is the value that we are searching for. We save the variable and we add the index, we add the new digit to our number string essentially, and we remove the indexes that we have lost for all the numbers in which this value is less than what it is. So left -1 will give us that range essentially, okay? And we again abstractly use our function here, and we remove this from k. And finally, the remaining indexes, if we use the remaining indexes -1, we will get the exact index of the digit in the number that we have discovered that we belong into, and we simply just output that character which is on that index, and that will be the answer essentially, okay? In my main function here, I also have this variable t here, which is just going through the queries, okay? So we just read how many queries we have, and we execute this doit function for every single query, as I said. So this is a per query solution here, okay? So if this video helps you and you understand how I'm using this function here, please leave it a like, subscribe to the channel, and if you have any questions, if you don't understand how this works still, please feel free to comment in the comment section below, and I will answer as soon as I can. Okay, so see you in the next one.